The second classifier we're going to be looking into in this class is NaiveBayes, and so NaiveBayes is again another type of classifier that will allow us to assign to a given set of features one of two or multiple labels. As you can imagine, NaiveBayes classifier takes that name because it's based on Bayes' theorem. So let me just do a brief overview of what Bayes' theorem is, and then we'll go directly into looking into the NaiveBayes classifier. So Bayes' theorem basically is a way of solving a conditional probability. So for example, think if you want to determine whether given size and color a fruit is, say, an apple or a banana or an orange, the way we solve this is with the formula on the right hand side. So basically to solve that conditional probability, we need to understand what's the probability of a fruit in the world being a banana or an orange or an apple, right? So on the other hand, we also need to understand what's the probability of the features that we are observing happening, and finally, what's the conditional probability of, given that we know that the fruit is a banana or an apple or an orange, what's the probability that a specific set of features will take place. Okay, so again, it's just a way of solving that conditional probability. So when we talk about a NaiveBayes classifier, what we really mean is basically a classifier that what does is that it computes all the different conditional probabilities for the classes that we have in our problem, okay, and that will classify a sample using those probabilities. So basically the way it works is that we need to compute for every single class. In this case it could be banana, orange, and apple. We will need to compute the probability that that class takes place given a set of observations, so given a set of size and color observations, okay? And once we compute all these probabilities, we'll be able to determine the final label. To compute these probabilities, we basically use Bayes' theorem, and the main component of the Bayes' theorem, or the more complex component to solve, is the other conditional probability, the probability that given a class, a set of features is going to happen. So given that we know we have a banana, what's the probability that size is going to be yellow, the color is going to be yellow, and the size is going to be, I don't know, 5 centimeters, right? And so to solve that, we can apply chain rule, but in the specific case of NaiveBayes, we can also assume independence of those attributes, of those features, and so this probability becomes much easier to solve because it can just be solved as a product of this set of independent probabilities. And so the core of a NaiveBayes classifier is just a table containing these different independent probabilities for each of the classes and sets of features that we have. And in the end, what NaiveBayes classifier does is that it computes again the conditional probability for the different classes that we have, and then the class or the label with the highest probability is the one that is assigned as a final label. More formally or mathematically, how can we express that? So again, the y predict is going to be the label or the class that we are predicting. So this could be apple or orange or banana. And we express it as being the v value, so the label that has the maximum probability, the maximum conditional probability. If we solve this using NaiveBayes, using Bayes' theorem, we can just substitute this with this formula, right? Then because the denominator is the same for every single label in our data set, we can just remove the denominator. And so basically what NaiveBayes classifier does is that it looks for the class or the label that has this maximum probability. And again, as I said before, this is just like a prior probability for a given class. So what's the probability that a fruit will be a banana or an orange or an apple? And then this probability here, this conditional probability here, can be solved, assuming conditional independence, can be solved just as a product of these individual conditional probabilities. And so what the NaiveBayes classifier is going to do is that it's going to compute all these individual probabilities and compute its product, and then basically for each class it will have a final value, and the probabilistic value that's the highest is basically the label associated to that is basically the label that is output as the final label for the NaiveBayes. Let's see an example. So let's manually do what any software package could do for you. Let's imagine that we see we have this table where we have students, different information for different individuals. Sorry, they might be students or not. We have information about their age, their income, whether they are students or not, their credit rating, and whether they buy a computer or not. And we want to answer the question whether a person will buy a computer or not based on a different set of information that we have. Okay, so what do we know? We know that the individual has 35 years old and an income of 50K. Okay, and we want to understand whether he will buy the computer or not. Okay, it's a binary decision. In order to compute that, okay, what we need to do, what we want to compute is, given that an individual is 35 years old and has this income, okay, what's the probability that he will buy a computer and what's the probability that he will not buy a computer? Okay, so what do we want to compute? We're going to compute the maximum value out of these two potential scenarios. Okay, the probability that given that he will buy a computer, the individual is 35 years old and 50K, and the probability that given that he will not buy a computer, the individual has these D features. Okay, again, what we are doing here is we want to compute the probability that given those features, the individual will buy or not. And then what we need to do is, following the NaiveBayes classifier that description that we offered before, we need to compute the maximum probability across these two potential cases. Case in which he will buy a computer, case in which he will not buy a computer. So what's the probability? Basically, to compute these two probabilities here, the probability that given those individual features he will buy or he will not buy a computer, we need to compute the probability of buying multiplied by the probability of given that the individual is going to buy the computer, the features appear, divided by the features that we have observed. Again, this is just simply Bayes theorem, okay? And we can even ignore PD because, that's common throughout, so we could ignore this last value. So we need to compute PH1, PH2, P of D given H1, and P of D given H2. And this is exactly what we're computing here. So PH1 is the probability that an individual buys a computer. If we take a look at the table, the probability that an individual buys a computer is 5 times over 10. And the probability that he doesn't buy it, if you count the no's, is 5 times over 10 too. We need to compute the probability that given the features that we've seen, the individual buys a computer. So you can look at the table and look for all the individuals who are 35 years old and earn $50,000 is a medium income, okay? So how many times an individual that has 35 years old has a medium income? It's 4 times, okay? So 4 times over 10. And so what's the probability that, the customer, given that he buys a computer, he earns this much and has that age? So we look for the yeses, okay? The individual here bought a computer, yes. It's medium and 35, okay. Bought a computer, it's medium and 35, okay. No, and bought a computer is medium and 35. So 3 times out of the 5 times that an individual buys a computer, 3 times out of the 5 times, the individual who is 35 years old and earns a medium salary buys a computer, okay? We do the same thing for the other one. So we look at the table and see how many times the individual does not buy a computer, and after looking at the no, we look for a 35 and medium here, okay? It's not, we have a no with 35 and medium here, and it's the only one. So 1 case out of the 5 no's that we have here happen. And once we have all these probabilities, we can basically just compute the probability that H1 will happen given D and that H2 will happen given D. And as you can see there, the probability of H1 happening given D is higher than the probability of H2 happening given D. So what this means is that for a customer who's 35 years old and earns a medium salary, around $50,000, okay, the customer will buy a computer. Okay, that's what the NaiveBayes classifier is doing. And this is basically the way we build a classifier. Okay, so basically we take into account all the different probabilities. The way the classifier is internally built is that it breaks up this table into different subsets of tables, okay? And it computes the different probabilities and basically, associates the final label based on the classifier. So after the example that we have seen in terms of, who would buy a computer based on age and income, I would like to basically go back to NaiveBayes classifier and cover how is training and testing done in any software package that you will be running. And so again, we assume that we want to predict a label Y that has different values. For example, in the example that we just saw, those values are going to be whether someone could buy a computer or not. So it's just a binary classification, but it could be multi-class as well. We also have a set of attributes, in our case, where things like, for example, income or age, okay? And then what the model does internally during training is that it needs to learn all the different conditional distributions, part of the Bayes theorem formula that we are solving. And so we're going to be learning, all the conditional probabilities of given a label, in our case, given that someone buys or doesn't buy a computer, what's the probability that we observe a certain feature is taking place, right? And on the other hand, we also need to learn what are the individual probabilities for each of the y's, which is also part of the Bayes theorem. And so the way we do this is basically we break all the data set that we have. We have a training data set and a testing data set. For the training data set, we break it into different subsets, and each subset is going to contain all the samples that have a given label. So for example, all the samples that have would buy a computer, yes, or in all the samples that have would buy a computer, no. And for each of those two subsets, we basically compute this probability, okay, which is basically prior probability of whether someone would buy a computer or not. And then at the same time, with all the samples in our training data set, we also learn each individual conditional probability. So given that we have someone would buy a computer, what's the probability that the income would be X? What's the probability that the age would be Y? Okay? And then basically, what happens internally during testing, during prediction, okay, is that given a set of features, given a set of x's, okay, the model is going to look for basically these individual probabilities that were computed with data from the training data set, and it's going to compute or to multiply these values for each single class. And then basically it's going to select the class label that corresponds to the highest probability. And that's the output that the NaiveBayes classifier is going to give during the testing, during the prediction process. Put another exercise here. Okay, it's exactly the same reasoning. You can try to answer this, do it as a homework at home. You also have the solutions here. So, try not to look at the solution before solving it. If you have any questions, just let me know, but it's exactly the same thing. Okay, and before we move into the example with R, I want to specify just a few small details. So something that might happen when you think about NaiveBayes classifiers and NaiveBayes probabilities is that, imagine, for example, the example that I was mentioning before about determining whether an email or whatever, a short message is spam or not. When we have our training data, it might happen that, some of the words that we have in our training data and that we associate to spam are there, but it might happen that some of the words that are spam words, we don't have them in our training data, simply because the training data cannot represent, all possible cases that we have there. So imagine that, our model, our NaiveBayes model, has taken all the training data that we have, has computed the different probabilities, okay? So for all the words that it has observed, so it's computed the probability of if it's a spam that the word buy appears, if it's a spam that the word Viagra appears, and so on. But suddenly, we get a new sample, the testing sample, and the testing sample has a word that the model has not been trained for because it hasn't seen it. Imagine that we get fruit. And the model NaiveBayes is like, well, I've never seen fruit. I don't know what to tell you. I don't know how to compute that probability. And so I don't know how to compute the argmax process and to, compute or give out the largest probability and the label associated to that. In order to avoid this type of situations, basically we will add a smoothing factor. Okay, so what smoothing factors do is that they basically account for the fact that in our training data, it's going to be quite difficult to have all the possibilities that are, that might happen out there. And so because of that, And because we don't want the model to break when an example that wasn't offered as part of the training process happens, okay, if we see something like this, then we want to add that smoothing factor. And the smoothing factor, there are different types of smoothing factors. The easiest or more straightforward one is the Laplace smoothing. And Laplace smoothing, basically what it does is that it adds what we call a uniform prior over all classes. So it's basically saying just add up, for example, 1 or any value alpha that you want to add up to all the different features that were not observed during training. Okay, so for example, if we have something like I don't know, we have a set of words, and for each word we have a probability of it appearing in a spam email. Then we take all the dictionary words, and for all the dictionary words that we have out there, we're going to add an alpha value. And what that alpha value is going to represent is, rather than having a 0 there that's going to break the whole classifier, we'll add a very small number. Okay. Obviously, what this means is that if we see that word highly probably will not be a spam. I mean, we have observed it very, very a small number of times, but it's just a way of acknowledging that that word exists. Okay. And again, it's just kind of assuming a prior distribution across the unseen words. So for all those elements that already have a probability associated, a counter associated, we're going to add up that alpha value. For all those that do not, the alpha value will be the counter that the model has there. Okay? To summarize, and before we move on to NaiveBayes in R, I would like to give a comparison between the two classification methods that we have learned in this class. NaiveBayes, remember that it's a generative model, so basically it's a model that attempts to generate the way the classification is done. Okay, and so basically it just doesn't learn how to separate two classes, but rather it learns how conditionally distributed those classes and features are, right? And so we need to learn one conditional probability to infer another one. Because it's precisely based on Bayes' theorem, NaiveBayes in principle is easier to compute. Okay, we don't need to do any learning of parameters like we did during the logistic regression. However, NaiveBayes makes really strong assumptions about conditional independence of the features that we use. Okay, and oftentimes that conditional independence doesn't hold in many of the problems that we look into, which means that we will not be able to use NaiveBayes. And on the other hand, a lot of related work has also shown that NaiveBayes work really well for small data sets, and so having larger sizes might also be a problem. On the other hand, logistic regressions, as we've also discussed, is a type of discriminative model. Okay, so it doesn't try to learn the distribution that actually might be explaining the relationship between X and Y, but rather it just learns a way of separating the two groups, of discriminating between the two types. The types of assumptions that logistic regressions make are weaker, okay? So in general, it's generally much more applicable to many other settings than NaiveBayes. But on the other hand, because we basically need to solve an optimization problem to identify what are the parameters for the logistic regression that we need to use, that actually requires a large number of training samples to be able to identify an accurate set of parameters for the model.